In your book, there's a table of rotational inertias or moment of inertias of different objects, spheres, rods, cylinders, and things like that. And there's equations for those. So the question is, where do those equations come from? Well, we've determined the rotational inertias of things experimentally, but how do you get an equation for those? So we're going to take a look at how that's done. It's a three-step process. I'm going to walk you through it. So I'm going to take an example of a ruler, and we're going to just take a ruler and we want to spin it around the center. It's around the halfway mark. And for that situation, we want to find the rotational inertia of it. So how is that done? Step one, we need to find a mass versus radius equation. So the easiest way to do that is to graph what the mass versus r looks like. So I'm going to take an m versus r graph here, m and r. And if the mass is uniformly distributed, then this graph should look something like this, linear. The more distance I go, the more mass I gain. And if this distance is L, the length of the ruler is L, and if I back this over here, I'll see this is capital M for the mass. We have something that looks like that. So the equation m versus r, m as a function r, is linear, so it looks like y equals mx plus b. So the slope times r, and the intercept is 0. So that's step one. Find an equation for the mass as a function of r. So this is pretty straightforward. Step two, we write the rotational inertia integral. So this is I is equal to the integral of r squared dm. Now, where this integral came to be and why it's r squared, not r cubed, is a different story, but we're going to use it right now. There's a little side dish with this. Step 2a is a little side dish. And what we want to do is we want to find what dm is. So dm dr is the derivative, which if you take the derivative of this equation, it's m over L. Therefore, dm is equal to m over L dr. dr. So I'm going to do a simple substitution, and I'm going to rewrite the integral as r squared m over L dr. And m over L is a constant that we can bring out later, but basically we do a substitution for dm. What we're doing is we're trying to find the rate of change of mass versus r. So for incrementally small changes in r, as I move along here, how much mass do I gain is what I'm really doing. How is the mass changing as r changes? And it changes as the derivative. So that's step two. We get to this point. We want to get rid of dm. Finally, we want to integrate using the appropriate limits of integration. So in this specific example, and we can do multiple examples here, I want to find the rotational inertia, moment inertia about its center, right there. So as it rotates about the center point. I could make the pivot point here, anywhere in between, the other end, but for this example, I'll put it in the middle. So for that case, when I integrate this thing, and I'll bring the m over L out because it's a constant, so this basically becomes r squared dr. This is going to be, from this center point, I'll call that 0. This is minus L over 2 to plus L over 2. So my integral is going to be from minus L over 2 to plus L over 2. And again, I could change the limits of integration based on where my pivot point is. So now we can integrate this relatively simple integral. This is m over L. This is r cubed over 3. Evaluated from minus L over 2 to L over 2 positive, which gives me m over L. Let's see here. I'll bring the 3. I'll leave the 3 there. I'll say this is what L cubed over 8. Excuse me. Yeah, this is 3. Minus quantity minus L cubed over 8 times that 3. So the 8 comes from the 2 being cubed, and the 3 sits out there. So I clean this up a little bit. This becomes m over L quantity, and these are going to add here. So I'm going to get the quantity 2L cubed over, and the common denominator here is 24. So I'm going to get an L cancel one of those to make it a square, and that's going to be a 12. So I get a final answer of m L squared over 12. So if I rotate this object about the center, the rotational is ml squared over 12. Again, I could change the limits of integration and get a different number. So I can determine rotational inertias without actually performing an experiment. I can do it using the rotational integral, rotational inertia integral as well. So those are the 3 steps you'd follow to find rotational inertias.